we doing? So we're in 3.12, right? I believe. Implicit differentiation. Okay. All right. So let's do a quick recap. So I know we did this a lot last time, but let's just kind of do it again. So like if I, for example, just a simple chain rule, let's say, let's say I have a function. Well, actually, let me do this just to kind of. Okay, so let's just say I have x squared minus 3 to the 4th, like that. Okay? So then, what's the derivative of f of g of x? Okay, so here, the inside function g of x is x squared minus 3, right? And then outside is x to the 4th. So so this is a pretty easy one, right, compared to the ones we did last time. So what is it? 4 times x squared minus 3 to the 3rd, right? Times 2x. Okay. All right. So the main thing that I want to get across here is that, so this is g of x, right? And this right here is g prime of x, right? So notice how when you do the chain rule, you leave the inside where it is, right? And then you multiply it times its derivative, right? Okay. Now, let's suppose, you have the following, okay? So let's say you have, something like this. Let's see. I don't know. Something like that. Now notice, what is g of x? Do you know explicitly what g of x equals? No, right? You're not told explicitly what g of x equals. Okay. But does that prevent you from finding the derivative of this function? No, right? So you can do this. So let's see. So there's a lot of parentheses here, but what would the derivative be? 7 g of x to the 6th, right? Times? Yeah. Okay, so notice that just because I don't know what the function is doesn't mean that I can't still find an expression that describes the derivative, right? And so that's basically what implicit differentiation is that, so for example, sometimes you have a curve, let's say, expressed implicitly. So for example, let's say you have 4x squared plus, I don't know, 16y squared equals to, I don't know, 64. What is that graphically? Not quite a circle, because it has different numbers in front of the x and the y. It would be it's an ellipse actually, right? So this is an ellipse. Do you guys remember how to put this in standard form, just for fun? Remember, you divide this by 64. So then you get x squared over 16 plus y squared over 4 equals to 1, right? Okay, so this is an ellipse, right? If I graph this, let's see, so centers at 0, 0. And then, do you guys remember? So this, you can rewrite it as 4 squared. This one as 2 squared. And so that means that you go 4 on the minor axis along the x, and then 2 along the y. And so then you can draw your little ellipse here like that. Okay, so what does that have to do with derivatives? Well, if I, so up to this point, have we ever found the derivative of an equation? Not a function, but an equation. No, right? Okay. But if you look at an ellipse, the ellipse is a curve. Do you think that I should be able to, for example, draw a tangent line at any point on the ellipse? Yeah. Sure, right? You should be able to find slope of the tangent line at any point and evaluate the derivative, right? Does that make sense? That you should be able to? Okay. So that's all implicit differentiation is. So, so what do you do? So basically, so this is what you do. So let's do it with the same ellipse. So let's say we want to evaluate y prime of x or dy over dx. So what is the dy over dx again? Derivative of y with respect to x, right? Okay, so I want to find the derivative of y with respect to x given 4x squared plus 16y squared equals to 64. Okay, so what do? So the first thing that you do is you find the derivative with respect to x of both sides. Okay, so you take, so let me just rewrite it here so that we have it. So 4x squared plus 16y squared equals to 64. All right, so if I, for example, write this, and I write that. Okay, so what's the, just before we continue, what's the difference between having d over dx and then the parentheses, like I wrote down right there, and dy over dx? What's the difference between those two? Meaning, what's the difference between this right here and this d over dx business? They both involve derivatives, but are they interchangeable or?
No. One's the derivative of y with respect to x, the other is just the derivative.
Close. But more important than that, take it a step further. What is the d over, when you have d over dx and then you have a parentheses, so we've written it down a bunch of times, but what is it really? That's the derivative, starts with an O and ends with an R. Nope. No, it's the derivative operator. Operator. And so remember, so, you know, just like when you have, so I'll erase this right now, but like if you have 4 and 3 and then you have a plus in the middle, the plus sign is an operator. It tells you to add the two numbers that you have, right? So in the same way, when you have d over dx like this is saying, okay, well, whatever you put in the parentheses here, take the derivative of that, right? It's telling you it's like an action. Take, you know, do something. In this case, take the derivative. It's not saying the derivative is, it's telling you to do something. Does that make sense? The difference between the two? Okay. All right, so let me erase this other business.
So dy over dx is the derivative?
Yes.
Okay.
So this is the derivative of y with respect to x. Yes. Okay, now, okay, so what is the derivative of 4x squared? 8x, right? Okay, so this is 8x plus, what's the derivative of 16y squared? Okay, close, but not quite. Because y is a function of x. So what rule do I have to use if I'm getting the derivative of a function? I have to use a chain rule, right? Isn't that what we just said over here? So this is why I did this little example over here, right? If I have a composition of functions, even if I don't know what it is, I have to use the chain rule to get the derivative of that, right? So that's why right here when we got the derivative of this, we said, okay, well, it's 7, leave the inside alone, right? The inside function, it's a function, to the 6. So we did the power rule, right? But then we had the chain rule where we multiplied it by the derivative of that inside function, yes? Even if we don't know what it is. Okay, so how is that the same as this? Well, I know that y is a function of x. Do I know what y is explicitly? No, right? And in this example is simple enough that you could solve for y and figure out what it is. But most of the time you won't know what it is explicitly. But you do know that it's a function. So when I get the derivative of this, it's going to be 32y to the 1, right? That's the power rule on the outside. Well, actually, I probably shouldn't put that because that looks like a prime. But 32y, right? But then times the derivative of y with respect to x. Or y prime, which often you write it. Okay, so does that make sense why that dy over dx is there? It's from the chain rule, right? Because y is a function of x, and so then when you get the derivative of this, you have to use the chain rule, right? So you do the power rule, 32y times the derivative of the inside. This is like the g prime that I just showed you, right? Does that make sense? Yes? No? You guys are looking at me funny a little bit. Okay, and then what is this equal to? 0. And can I find dy over dx, which is what the question is? Sure I can, right? So if I solve for dy over dx, what would I get? I would get dy over dx equals to minus 8x over 32y, right? Or what is that? Minus x over 4y. Now that's a little bit interesting because we have x's and y's in there, right? And so, well, that kind of makes sense though if you look at the picture. Because, well, let's write down, I did it, but I didn't write down the second step. So second step is the derivative of both sides and then solve for dy over dx, right? Okay, so now if I just kind of draw a rough sketch here, this is what it looked like, right? Notice if I tell you, for example, so this was 4, right? This is 2. If I told you what's the tangent, what's the slope of the tangent line at x equals 2, what would you say? Which one, right? That's why you need an x and a y. Because if you look at it at x equals 2, well, there's this point on the ellipse and there's this point on the ellipse. So it's vague. So that's why you would need both an x value and a y value to say what the slope of the tangent line is. Does that make sense? Any questions with that? Thank you. Okay. All right, let's do another one. You guys ready? Okay. Let's do one that we, a little bit more complicated one. Let's say we want to, let's see. So dy over dx again. How about, let's say we have x cubed minus 2xy equals to sine of y. Well, let's throw a squared in there just for good measure. Okay. So what's the first thing we do?
Take the derivative.
Derivative of both sides, right? Okay. So derivative of both sides. All right. Now, what do I get here? 3x squared. Okay, so no big deal, right? And then what about the next one? Minus 2. What's the derivative of x? 1. What's the derivative of y? Bless you.
So much.
Is that right? Because the derivative of x is 1, the derivative of y is 1 times dy over dx, right? Nope. Nope. What's wrong with that? Product rule, right? You're multiplying two functions. You're multiplying x and you're multiplying y. So when you get the derivative of the product of two functions, you have to use the product rule, right? Okay. So let's take a step back. So no big deal. We can do that. So let's see. So what's the derivative of, let's say we combine 2 and x together. So the derivative of that is 2 times what? Okay. And then what?
Plus the derivative dy dx times the first one.
So 2x times
dy dx.
dy over dx. Does that look okay now?
Yeah.
Almost. Almost.
Negative.
Negative, right? Careful with the negative. So notice you're subtracting the product rule, right? So either put a parentheses around the whole thing like that, or probably easier, just distribute the negative. So this would be a minus 2x dy over dx. Okay, now a lot of students get confused and then, and for example, say, well, why isn't there a dy over dx right there? Can somebody tell me why there is not a dy over dx there? Because we did not take the derivative of y at that point, right? So that's when, because why is it that you multiply by dy over dx? It's from the chain rule when you get the derivative of that inside function, right? So in this, in this part right here, I got the derivative of, this was the derivative of 2x, right? And so that's how I got the 2, and then I multiplied it by y. Does that make sense? So we did not get the derivative of y at that step. Any questions with that? Does that make sense? Just that part right there?
So the y itself, when you have 2 times y, the y is just left alone? Is that what you're saying?
Yes. But see, what is y? Y is some function. Do we know what it is explicitly? We do not know, right? And even if you try to solve for y in this one, would you be able to? Is it possible to solve for y explicitly? No. It is not possible. Because you have linear and then you have a trig function inside it squared. There's no way. You're not going to solve for y. It is not possible. So all you know is that y is a function of x, so that when you get the derivative of it, then you have to use the chain rule. Yes? Okay. All right. So let me get rid of this stuff so it doesn't clutter up. Okay, so now what does that equal to? Cosine, yep. Cosine of y squared, good. Times 2y dy over dx, exactly. Yep. So it's a chain rule. I apply the chain rule twice, right? Okay, now how am I going to solve for dy over dx this time? I've got 2 different ones. Same sign and factor, right? So do some algebra stuff here. So if let's see. I might as well. Let's leave 3x squared minus 2y there. And then on the right side, I'll do cosine y squared. Is it okay if I put the 2y right there in front?
Yeah.
And then plus 2x. So just move this 2x right here, right? Just move it over to the right. And then factor out the dy over dx. Right, so just move the 2x dy over dx to the right, and then factor it out. So far, so good? Okay, so then what is dy over dx equal to? Mm-hmm. Divided by all that stuff, right? Okay, so that's the derivative right there. So what do you guys think? Yes, questions?
So when you take the 2x times dy dx over to the other side, where does the dy dx that was attached to it go?
Well, I just did 2 steps in one because I was running out of room. But you move it and then you factor out the dy over dx, right?
Oh, okay.
Yeah, so I mean basically right here, both of this term right here and this term have a dy over dx multiplying it, right? And then you just factor it out so that you can divide by it. Okay, do you guys have any idea what this looks like? If we were to graph it. No. How can we graph it? Desmos. Magical Desmos. I think Desmos can do it. Your graphing calculator can do it with a little finagling. But let's see. Let's see what Desmos tells us. X cubed minus 2xy equals to sine of y squared. Wowzers. So that's pretty crazy, right? So let's say should we find the equation of the tangent line somewhere? Let's see. We got to pick a point somewhere. But how do I thought it would give me a point, no? Doesn't it normally?
You have to click on it, or you
Clicked on it. See?
Click and drag.
Maybe it's too confused to give me a point.
probably just makes your drunk graphic.
Yeah. Okay. All right. So we're gonna write down this number. What is this? That's 1 and 0.4. 0.415. Right? Well, isn't that? Oh yeah, you guys can't see it very well. Oh wait, I know. Don't I do this one? Projector mode? Is that better? Okay, so that's 1 and then 0.415. Okay, we'll do that. And we'll test it out. Okay. So you guys remember? 1. So let's add on. So question add on. Add on. Find the equation of the tangent line at x equals 1 and y equals 0.415. Okay, if it doesn't work, then that means that I need glasses or something. Okay, so what do I do? Plug what in? Plug in x into where?
Y is one in this first.
Plug in something somewhere. We'll get something, I promise. No. Now, okay, so what does this tell us right here? So this is the derivative, right? That'll give us the slope of the tangent line, right? Okay, so notice it has x's and y's, right? So we need to plug in both x equals 1 and y equals 0.415 into there, right? Now, I don't have a calculator, but I guess I can go back to my trusty Desmos here, which, okay, let's see here. So 3 times 1, oh, well, I don't need to do that. Okay, it's 3 minus 2 times, no. Okay, 3 minus 2 times 0.415, right? And then that divided by 2 times 0.415 times cosine of 415 squared.
So we're supposed to plug it into the original?
So what is this? So the expression that I just wrote down right now, this one right here. What is that? That's the derivative, right? That's not the original. So those two functions are not the same. The one on top, that's the graph, right? That weird graph that we just saw. The one on the bottom is I took the derivative and I just plugged in x and y, right?
So now 0.77 is our slope.
That's the slope, exactly. So so the slope is 0.77012, all that jazz. Okay, so let's write that down.
Why is it 3? Shouldn't it be 1? Oh, yeah. Oh.
Yeah, you with me? So the slope. Oh, wait, have you guys seen this notation? This is good to introduce. Good point. If I do this, dy over dx, I put a vertical bar like that, and then I put 1.415. What does that mean?
The derivative at that point.
Yeah, so it means evaluate whatever is there, right? Dy over dx, evaluate it at 1, comma 0.415. Have you guys ever seen that notation? Probably not, right? So it's important. Good to know. Okay, so what is it? 0.770. What was it? 1, 2?
12596.
Okay, 1, 3. We'll do 5 decimal places. That'll be good. Okay, and then after that, then what do we do?
Solve for the line.
So now we can write down the equation, right? So what's the equation of the tangent line? Yeah, so there's 2 ways to write it. Since I'm running low on space here, it would be, well, I'm going to do this one. M x minus x naught plus y naught. Yes? Why not? So y is equal to 0.77013 times x minus what? My x value, right, which is 1, plus my y value, which is 0.415. Okay, so this is the equation of the tangent line. We hope, right? Okay, so let's graph it. Let's see if we got it right. We better, right? So let's see. Y is equal to 0.77. Copy paste. Okay. Times x minus 1 plus point. Oh, snap. Look at that. Beautiful. Beautiful. So there it is. That's it. So pretty cool, right? Yeah.
Would this be useful for anything?
All kinds of stuff. What's this negativity about?
No, like the graph.
Oh, this graph. Well, yeah, it's like art. There you go. Exactly. It's like art. Okay, I'm going to give you guys one to try. You guys ready? So here you guys got the derivative, right? Of all this stuff.
Well, this right here is just what we did the derivative of this, but because it's
Okay. So on the left side, this is 2x plus 4y dy over dx, right? Here, notice you have to use a chain rule, right? So you bring down the 2.
yeah, it'll be 2y.
Oh, yeah. Sorry. Yeah. Sorry. Okay. Sorry about that. So 2x squared plus 2y squared minus x. Like that, right? So right now we're doing good? Okay. Then times the derivative of the inside, right? So times, whoa, wrong tool there. Times, so what's the derivative of 4x? Good. 4y. Okay, so this is where most of you guys got tripped up. So notice right here you have a y and you're getting the derivative of 2y squared, right? So what's the derivative of 2y squared? Well, it's 4y times dy over dx, right? Right here is where the dy over dx goes. It does not go at the end after you just do everything. You just tack it on. You do it right when you get the derivative of y, right? Does that make sense?
So the 4y and the dy dx could go in their own parentheses together then. Is that correct?
No.
No? Because they're the ones that are being multiplied together.
I mean, you could, but you do it first anyway, just by the order of operations.
You mean they could go in their own parentheses. Do you mean like that?
Yeah.
Oh, yeah, that's fine.
Okay.
Yeah, that would be okay. Minus 1, right? Like that.
Yeah.
And then that's it for that. Okay, now how do you proceed from here? It's a mess.
You don't give up.
You have to distribute. So you absolutely, positively have to distribute all this.
It's like it's implied that it's
There is no other way.
but I don't want it. Like I know it's supposed to be distributed.
You said these were fun.
Can I just put like all of it in one piece?
Okay, I'm going to give you guys a pro tip. Are you guys ready? Pro tip. Okay. Pro tip. You guys ready? You guys are going to thank me in a minute. You guys already did the pro tip? Okay, so notice the question does not ask us to find dy over dx. The question asks us to find the equation of the tangent line, which means that we need basically the slope, right? Which is a number, yes? Okay, so instead of solving for dy over dx in this whole mess, plug in x equals 0 and y equals 1/2, and then solve. Because that'll give you the slope as a number, and then you'll be able to find the equation of tangent line. Does that make sense? What is it? Okay, so I'll give you guys another couple minutes to do it. All right, so let's see. All right, so let's figure this out. So we've got, if you plug it all in, you get this mess, right? So this is 0. So I'm gonna get rid of this 0. Yes? Okay, what else is 0? This is 0. Bye. And that's it. All right, now 2 times 1/2 dy over dx. That's 1 dy over dx. Yes? Okay, now here I have 1/2 squared. What is that? That's 1/4, right? Times 2? 1/2. 1/2 times 2 equals? So all that is the number 1. Okay, Then what else do I have? This is 4 times 1/2, which is 2 minus 1, right? So then 1 times this is just that, right? So then dy over dx equals to positive 1. Yeah? Okay, now, just right here in this corner, I'm going to write down the equation of the tangent line. So tangent line, y equals to 1, 1x. Oh, I guess, yeah, so that's easy. So x plus 1/2. That's it. Done. Finito. Adios. Okay, questions?
Is this gonna be on the test?
Of course. Why else would we do it? Well, to learn, of course. But yes, it will be on the test, for sure. Yes? Yeah, because we're just looking for the equation of the tangent line. If the question was find dy over dx, then we would have had to distribute everything and do all that. But I wouldn't give you one this messy. I mean, that's just ridiculous. I mean, you should be able to do it, but I won't give you one because it'll take like an hour to do. I mean, not really, but
But yeah, please don't.
yes.
Would anything change if I just plugged it in the beginning of everything?
Yes, because you wouldn't be able to get the derivative.
No.
Because if you plug everything in, then you just get a constant. Then there's nothing to do. Any other questions? No? Okay. All right.